working on this bell work. It's in your packet. So let's see here. Hey, Brooke Jones. Brooke Jones, can you hear me? She's giggling about something. She's like, now she's giggling. Now she's red in the face. Oh, my.
Okay, what?
Oh, my. Okay, what separation technique would you use if you want to separate things based on their boiling points?
Distillation.
You got it. Yep. Got to distill it. Little abbreviation. Thank you, Ms. Jones. All right, let's see here. What about some Genamusa separation technique for differences in density and solubility? Yeah, I'd go to the centrifuge on that one. Because you need, you definitely need to have a difference in solubility for a centrifuge to work, but a difference in density, it can also work with that as well. Okay? Love it. All right, Kelsey Schmidt is a separation technique that uses the differences in solubility only. You got it. Filter it, baby. The filter doesn't really take into account the density of anything. It just takes into account is it soluble in water or not. Because if it's not, it's getting stuck in the filter. And then that means the last one, differences in color, we're talking about chromatography. I'll just put chrome for short because my handwriting is big. All righty. Distillation can be used when you have a mixture of, we'll probably go with liquids or dissolved solids. It won't really work with just a straight up solid most of the time. Mr. Patak and I had an interesting conversation on that one, but usually that solid isn't going to melt with just a little flame you have there. So it probably won't work. It won't get hot enough really. You could make that happen in some circumstances, but most of the time we're going to be talking about liquids and dissolved solids. Okay. So for example, the orange food coloring and the peach scent and the water and the dissolved sugar in the peach pop from yesterday. Okay? Centrifuge can be used when you have a mixture of liquids and solids, but not dissolved solids. Because if it's dissolved, it's not soluble. Or, I'm sorry, it is soluble. And so the centrifuge, you can spin around as much as you want, but you're not going to get stuff to undissolve or something like that. Okay, so it's not really going to help you. But you have two things that don't dissolve well with each other, or you got a solid and a liquid, or you have two liquids, but one of them's insoluble, then you can work with that. Okay? Filtration, we could be working with solids and liquids. This also won't work with dissolved solids. Remember the food coloring? I think Kelsey, I was bugging about this. Food coloring is what in water? Soluble. If it's soluble in water, that means it goes right through or gets stuck in the filter. It'll go right through it. Okay, so dissolved solid, you can try and filter if you want, but it's going to go right through that filter. Part of the reason why that is, if you want to picture something like, where'd my little picture go? So let's say I had some Kool-Aid, okay? When I pour it through the filter, this Kool-Aid is stuck in between all the H2O, so it just sort of slides through the holes of the filter in between the H2O, so that's why when we have something dissolved, it doesn't really get filtered out, okay? So that's the kind of picture that I sort of give to folks. What about, we'll hit some of the heavy hitters on, let's see here, the back of your bell work. So this is the bottom half, I think, right? Is this the bottom half or the back?
One is the bottom.
One is bottom half, okay. Identify how you would separate and mixture the following materials: styrofoam beads, iron shavings, and potassium bromide. Let me see here. I gave you guys the densities. I told you a little bit about them. Like, this is a solid. It's not soluble in water. Its density is blah, blah, blah. So let me see here. Who has an idea for this one? What would you do? Yes?
I would use filtration to separate the potassium bromide from the other two, because it's soluble.
Oh, I see. Well, one thing you have to do before that, so if you were to start with the three solids, if you use a filter, you pour them all in there and they'll all get stuck in the filter. What do you have to do before you even filter?
We mix it with water.
Mix it with water, okay? So that's probably the first thing I'd do. I'd probably add H2O, which will then dissolve your potassium bromide. So then you went with filter?
Yeah.
Okay.
And then I would, I use a centrifuge to do the other two because they have different densities.
Okay. So maybe centrifuge Center. Okay? Did anyone else write something different? Because there's another way to do this. There's actually a few ways to do this.
Chuck all in a centrifuge.
Haha. What if you did this? What if you first drag a magnet through this whole sample and you get all the iron out that way? You get all the iron out that way, right? Okay. Then you could add the water, and then you could filter it. So then you have your potassium bromide it goes through the filter. Your styrofoam beads get stuck in the filter, and you're done right there too. So there's another option. Okay, there's always a few options. Well, I shouldn't say always. There's usually a few options. Okay. Yeah, not bad, not bad. This is a nice thinking outside the box question. You'll often get a question like this where I just sort of list some properties of what you're working with, and you sort of have to figure out, okay, well, I could do, if I do that, then step 2. One thing to not forget, don't forget that add water. That's a common one that people forget, because they're like, oh yeah, so you just pour it through the filter, and I'm like, pour what? Like the solid chunks of iron and potassium bromide? You gotta remember, like, pour water in there, mix it up, and then you can filter, or then you can do various other things. All right, not bad. Let's see here. Colin Lee, how are we separating those noodles out of the boiling water? It's a mixture of water and noodles.
I would just put through a filtration system.
Yep, I'll just filter it. It's called a colander. It's probably a big bowl that your parents have under the sink or something like that. It's got holes in it. You just pour the boiling water with the noodles in it. The water goes through. The noodles get stuck. The end. Yep. Filter. And let's see here. Yeah. We'll move past these for now. You should be able to answer the rest of those. But let's go ahead and get to our notes for the day. The law of conservation of mass. So go ahead and get out them notebooks. Go ahead and get out them notebooks. And don't you worry, period 4 or 5 virtual folks. I'll be calling on you people at some point. I'm just noticing that Maya Hillberry has a panda icon with its hand up in the air. Huh. Totes adorbs. Alright, anyways. Law of conservation of mass notes. The matter notes part 4. At the end of today, we will have learned all of our stuff for the Unit 2 test, which is on Thursday, not Friday. Tomorrow will just be all review. Okay, and I'll give you an overview of the test. Here's how many questions it is. Here's how many points it is. We have to finalize the test later today after school. So, all right, here we go. What happens to the mass of a candle is it burns for several minutes. So, I've got a candle here. I have it on a little scale. So, you virtual folks, maybe you can see this. Got my little candle. Okay, I'm going to go ahead and zero this. Hamdi, will you come up here and tell me what mass the candle is, pretty please? Just so everyone knows I'm not lying.
77.23.
77.23. Hamdi guarantee. There we go. All right, there we go. So that's the mass of the candle. So what I'm going to do is I'm going to light this turkey for the period. Now, my question for you, this is just a guess. You don't know. Will the mass of the candle increase? Will the mass of the candle decrease? Will the mass of the candle stay the same? So at the end of the period, when I get the mass of this, what will the mass be compared to 77.23? Just, huh? Nope, just put a guess down, A, B, or C, and we'll see if you're right at the end. I put Q, thinking outside the box. All right, sweet. We will come back to this. Okay. Now we got to go over a few things about liquids and solutions, okay? So a lot of folks will use the words liquid, solution, water, all that stuff is like interchangeable, but they all have their own specific definitions, so we got to clarify. A liquid, which if you see little parentheses with the lowercase L in it, that's referring to a liquid, that's saying something is a liquid, is a pure substance. This is talking about a state of matter. So pure H2O is a liquid. Okay, it's a liquid. Pure H2O is a liquid. So like H2O, or if you had some pure ethanol or some pure mercury. Mercury is a metal that's liquid at room temperature. Fun times. Now, a solution is a homogeneous mixture of dissolved ions. Okay? A solution means you have more than one thing in the container. It's mixed evenly, okay? But something is, you got more than one thing because it's a mixture, and something's dissolved in there, okay? Sugar water, for example, would be a solution because it's a homogeneous mixture of dissolved ions. Now, to clarify, an aqueous solution, so we're coming from that base aqua, AQ, that means it's a water-based solution. And basically all solutions in this class will be water-based. So if you guys look over there, those cabinets right over Jenna Moose's head, every single one of those plastic bottles has a aqueous solution in it. Okay? They're all a water-based solution. Or these guys, for example, my magnesium sulfate, sodium hydroxide that I'll use in a demo later today and that I used yesterday. These are solutions where I have sodium hydroxide dissolved in water. So this is an aqueous solution. This is an aqueous solution. Okay? So homogeneous is a mixture of dissolved ions. Then we got aqueous solution. And notice that this has a little its own symbol, AQ in parentheses, just like this has an L in parentheses. So if you see the name of something and it has a little L after it, that's telling you, hey, this is a pure liquid. You see the name of something that has a little AQ after it, that's saying, hey, this is a solution, a water-based solution of whatever it is. So some examples: Kool-Aid, salt water, all the solutions we use in class. And you don't have to write that down, but you should be able to tell me what are some examples of aqueous solutions. And like I said, there's like about 30 or 40 different ones up there in those cabinets. Now, gases are represented by parentheses, little letter G, and solids with a letter S. They have their own designation. Just please note the things I have circled in green here. Those are abbreviations to tell you what state a chemical is in, whether it's solid, liquid, gas, or an aqueous solution. The most common one you'll see is probably the AQ. Most of the things we work with are in aqueous solutions. That's because it makes them easy to work with. You can pour them, that kind of thing. So we kind of like having that. And you can control the concentration a lot more easily, too. But yeah, it's pretty straightforward. L is liquid, G is gas, S is solid. This is probably the only one that's a little new to you, aqueous solution, AQ. But everything else is pretty straightforward. All right. So now we got to talk about equations. So I want you to go ahead and write down magnesium sulfate, AQ, plus sodium hydroxide, AQ, with a big arrow, and leave some space over here. So you want to take like half your paper with these two guys in the arrow, and leave some space over here because we're going to write quite a bit. So just like in math, chemistry has its own equations. There are chemistry equations. Chemistry equations. My guy's sweet dad joke coming up. It's going to be so good. So good. I can tell that Connie is thrilled to hear that dad joke. She can't wait. She sends me emails talking about how funny my jokes are in class all the time. She's like, yep, that's right. He's telling the truth. He's not a liar. Good stuff. Okay. So, when we have an equation like this, we will see a little do-si-do type action, where the magnesium on the other side will pair up with the hydroxide, and the sodium will pair up with the sulfate. So here's what's going to happen. This will become magnesium. Notice I kept it in red writing. Hydroxide plus sodium sulfate. And notice some things that we're already seeing. We're told that magnesium sulfate is an aqueous solution. We're told that sodium hydroxide is an aqueous solution. We're told that magnesium hydroxide is a solid. Okay? And we're told that sodium sulfate is an aqueous solution. In other words, if I take some magnesium sulfide and dump it into some sodium hydroxide, I should get some sort of solid to form. Okay? This equation helps me know that in advance because this little s tells me, hey, this is a solid. All right, some other labels. All the stuff before the big arrow, those are called reactants because they are reacting. They're called reactants because they are what is reacting. All the stuff after the big arrow, those are called products because those are what are produced. And it's all about where the big arrow is. That big arrow itself is called a yield sign. And you can basically think of it as the words to produce. Or you can think of it as sort of chemistry's equal sign. Okay? So like in math, you have like blah, blah, blah plus blah, blah, blah equals blah, blah, blah plus blah, blah, blah. So let me read this left to right in a chemistry fashion. Aqueous magnesium sulfate will react with aqueous sodium hydroxide to produce solid magnesium hydroxide and aqueous sodium sulfate. Okay, so I just sort of read that like a sentence going across there. That's what we are writing in this equation. Okay? That's what we are writing in this equation. So, don't forget that when we have a solid form, I have a solution that's called a precipitate. So you've already learned that term before. But the precipitate in this reaction would be this guy right here, magnesium hydroxide. That's a solid that's forming out of a solution. So our precipitate soluble. Anyone know the answer to that? Is a precipitate soluble?
No.
No. If it was, it would stay dissolved in the solution, right? But since it's not soluble, that's why the solid forms and falls out of the solution in the first place. So kind of by definition, a precipitate is insoluble. That's pretty important, especially if you start talking about separation techniques. You need to know that a precipitate is insoluble, which tips you off, oh, I can maybe centrifuge that. Oh, I can maybe filter that. Oh, I could not distill that probably. See how that kind of ties in? Okay, so no, they're solids, they fall out of solution. Okay? Precipitates are not soluble. So how can I separate that? Well, we just started talking about that. Filters are centrifuges because they're insoluble. So yesterday you saw me, remember the centrifuge? I poured these two things together, we got that white solid. I used a centrifuge to separate it. I could have used a filter. Hey, what type of change is this when you have a precipitate form? What type of change is that? Chemical. Can anyone give me a reason why it's chemical? What's that? That could be a phase change too. There is something there though. You're kind of on the right track. So we have a new substance formed. Okay, this is a brand new substance because we made magnesium hydroxide. That's not anywhere on the left side. Okay, this is brand new. So this sign of a chemical change. Hey, what else did you guys see when I did this yesterday? When I poured those two beakers together, what else did you see? Color change, right? It became white. So again, that's another reason why we had a chemical change. Evidence, solid formed and color change. Hey, check out this joke. If you're not part of the solution, you're part of the precipitate. Do you guys get it? Do you guys get it? Jeremy, do you get it? Isn't that so funny? Oh, man, Jeremy's laughing so hard he had to turn his mic off. Stop crying, Jeremy. I know it's that funny, but, get it together. All right. Okay.
What was the joke?
What? If you're not part of the solution, you're part of the precipitate. Do you get it? Because precipitates are insoluble. Do you get it? Boom, roasted. Whatever. It's really, really good. Hey, would you be able to filter out Kool-Aid out of a drink?
No.
Why not? It's soluble. It's soluble. No! It's soluble, right? So again, you couldn't filter it out because it's dissolved in the water. Filtering only works on insoluble solids, okay? And so that kind of reminds me of the picture. I already showed you guys this. Remember those little Ka, little Kool-Aid molecules, okay? They're going to be sort of trapped in between the H2O. So when you pour that into the filter, they just kind of ride the wave of H2Os right on through. Okay? All right. So back here, let's talk about the mass. So I have magnesium sulfate, magnesium hydroxide. I'll pour these on my little scale over here. So here goes some sodium hydroxide. Here goes some magnesium sulfate. Boom. All right, so I'm going to go ahead and get the total masses real quick on my little balance. So this here, is that more than 100 grams? It is. More than 200? No. You guys remember having to use these in elementary school?
Oh,
No.
You never had to use this in elementary school?
I've never seen one of those before.
What? When you go to the doctor's office, don't they use one of these on you?
maybe.
What? Where they like slide the little thing over?
Oh, yeah, they do that.
Yeah. Well, that's what this is.
It's
Only
slightly bigger scale.
it's a little bit bigger. I could maybe put like half of my foot on top of this. All right, let's see here. We're looking at. Come on. Come on. Okay, so go ahead and write this down. 175.77 grams. 175.77 grams.
Anyone tell me how these safe things?
37. Okay. So, I'm going to pour these two things together, and we are going to have a chemical change because we're going to have this new solid form, magnesium hydroxide, okay? It's going to be in a clear aqueous solution still, which is the sodium sulfate. So let's see here. I'm going to pour these two together. What will happen to the mass? You think it'll go up, down, stay the same? I heard some down, heard some stay the same. All right, well, let's see. Here we go. It looks like I went down a little bit.
Don't we put the other cup on?
Oh, yeah. Forgot. And it's exactly what it was before. It's exactly the same. I was like, am I going to catch people sleeping? So the mass is still the same. Even though we had a chemical change, evidenced by a precipitate and a color change, okay? So some chemistry happened there. We still have the exact same mass. This brings us to the law of conservation of mass / matter. This is a big idea. You better know this. You better know this bell ringing. Law of conservation of mass. Matter cannot be created or destroyed. Matter cannot be created or destroyed. The mass before equals the mass after. The mass before equals the mass after. So whatever mass you started with, you have to have that exact same mass afterwards. There's nothing you can do to not have the exact same mass afterwards. It is impossible. It is impossible. So if you start with 10 grams before, you better have 10 grams at the end. And I don't mean you better like make sure you sprinkle on a few extra grams in case you lost some. Like, no, you will have 10 grams.
Or you did it wrong.
Or you've broken the laws of conservation of matter and physics and life, basically. But you might as well try and jump up and see if you can defy gravity, okay? It's just not going to happen. So 6 billion years ago, when our Earth was formed, okay, the universe was made, let's say the universe had a total of 100 grams in it. It still has 100 grams today, and in another 6 billion years, it'll have 100 grams still, okay? It's obviously a lot more grams than that. But the point is, whatever mass we started with in this universe, that's the exact same amount of mass we have right now, and that will be the same exact amount of mass we have in the future. Law of conservation of mass, baby. Let's go back to the candle. All right. So what was our original mass of the candle? Let's see here. Where how many have me write that? 77.23. 77.23. I'll rewrite that. So it was 77.23. So that was original, whatever. Final mass. How many come back up here and read it? I never touched it. 75.91. 75.91.
Oh.
We lost about 1.32 grams. I want everyone to think about this in their heads for now. But does this violate the law of conservation of mass? Like Mr. Pilcher, you just said the mass before has to equal the mass afterwards. How did the mass of the candle disappear? So think about it in your heads for a minute, okay? Think about it in your heads for a minute. What the heck?
I'm already out.
He's like, I'm on this. I'm on this. Think about it in your heads for a second. What happened to that mass? Did I destroy the mass of that candle? What the heck? Blowing minds. I'm going to call on one of you virtual people first to see if you guys can answer this for me. Ooh, who's it going to be? I see all these names. Oh, I made my pick. All right. Maya Hillberry with your little panda and its paw up. Do you have any guess? Give me some sort of guess.
It decreased because some of it evaporated.
Ooh, some of what evaporated?
The melted candle wax.
Oh, wow. That's exactly what happened. Look at you, smarty pants. Okay, the mass was not destroyed. It just is in the air now. So there's actually a little bit of candle wax, burnt candle wax, in this air.
Let's go.
That's what happened.
Love breathing out.
Love breathing it. The wax vaporizes into a flammable gas, which burns. And so the mass leaves in the form of different gases. You don't have to write all of this mess down. CO2, H2O, and a little bit of soot and smoke. So it's no longer like candle wax as we know. It was chemically changed in a few gases, but it's in the air, okay? So maybe Kanaya Johnson over there, she's like, ooh, and she breathed in a little bit of CO2 that came straight from this candle. Okay? In fact, every time you can smell a candle scent, you just breathe in some of the CO2 that the candle gave off. That's how you can smell a candle. Just because some of that came off in the air.
Body freak out, but it's CO2.
Huh? Your body has breathed in CO2 every breath you've ever taken in your entire life. So, probably not. If it did, that would be a real bummer. Now, this demo usually doesn't work very well. It's kind of hard to do. But theoretically speaking, if that is truly mass on there, coming off the candle, I should be able to relight the smoke if I do this right. So I should be able to light this candle by the smoke. It's kind of hard to do. We'll see. Gotta get my aiming flame ready. So we'll see here. Oh my gosh. I'm not getting my birthday wish. What? Oh, did you see that? It's kind of hard to, like, I got close to it, but I didn't actually light the wick. Let's try it one more time. Maybe if I move this over here, is that better, Hamdi? Okay. That is unbelievable.
It's a trick candle.
See that? So you can actually relight a candle by the smoke itself. Could you nerds see that virtually? Could you kind of see it a little bit? Okay, sweet. Sounds pretty good. My goal is to, I was playing earlier with like a long distance tube to see like how far away I could, like if I got the smoke to go through here, can I light it from down there? So I was playing with that earlier. I might try that towards the end of the period. We'll see. All right. Well, let's see here. We got 5 minutes. Here's what I want people to do. I want you to do one of two things. I want you to either start working on this bell work, matter bell work number 2, or if you forgot to do your quiz yesterday, which we didn't talk about at the end of class, if you guys didn't do your quiz yesterday, you might as well go take care of that now. 3-question quiz. There is no 3-question quiz for today. There is no 3-question quiz for today. There's only one this week. So virtual folks, I would like you to work on this bell work the last 5 minutes of class, and then we're getting out of here. Live folks, if you didn't do your virtual quiz yesterday, go ahead and take care of that now. But if you did, work on this bell work right here.